Assalamualaikum and good day everyone. In this video, I'm going to explain about Ampere Circuital law or ACL. The ACL is actually quite similar to the Gauss law in electrostatic field. Okay, now let's recall. Let's recall what you have in the electrostatic. In electrostatic, you learn about Coulomb's law and Gauss law. While in the magnetostatic, you learn about Biot-Savart's law and Ampere Circuital law. So from here, I can give an analogy where the Coulomb's law is similar to the Biot-Savart law, while the Gauss law is similar to the Ampere Circuital law, where the ACL, we have the step to solve as what you have in the Gauss law. Okay, before we proceed, let's take a look what is actually the ACL. Okay, first, the ACL is an alternative to the Biot-Savart's law. Okay, the second point is we can use ACL to solve infinite current source. Okay, in this course, in the previous chapter, what are the sources that you already learned? Yes, it's about the line, the surface, and the volume sources. Okay, and the third one is the step. Okay, the step to solve the ACL is quite similar to the Gauss law. So this is the information about the ACL, where it is alternative to the Biot-Savart law, and we can apply the ACL to solve the infinite current sources, and the step to solve the ACL is quite similar to the Gauss law. Okay, now please recall the example 1 that I share with you during the explanation of Biot-Savart's law. Okay, where in that example 1, okay, we get the equation of H where it is equal to the I over 4 pi r sine alpha 1 plus sine alpha 2, where this equation is come with a diagram. Okay, where in the diagram it shows that this is the I, okay, and the H that we want to calculate is at this particular point, thus the R link it, and here we can get the alpha 1, and this will become alpha 2. Okay, so this equation is referred to this diagram. And what happens if this I is infinite? It means that this I is very long. Okay, it's infinite. Okay, this will give the value of alpha 1 and alpha 2 equal to 90 degree because it's very long line, okay, parallel to this I. Thus, H for the infinite line will become I over 2 pi r. So this is the H that we get using the Biot-Savart's law. So next, what we want to do is we want to find H for infinite line using ACL. After that, we are going to compare with this equation. Does it give the same equation or not? Okay, let's say we have I here. Okay, this is our I. Okay, and the I is to the positive infinity where it comes from the negative infinity. Okay, and now the question is find H using ACL. So this is the question. Okay, take a look at the step. The first step that you need to do is to choose the coordinate system. In this case, since this is a line charge, thus the suitable coordinate system is a cylindrical. Okay, let's say we plot this is our x direction, this is our y direction, and this is our z direction. Okay, the second step is we need to identify the location of H. Okay, in this case, let's say this is the location where we want to find the H. Okay, now we go to the third step. Okay, the third step of ACL is we need to build Amperian loop. Okay, if you recall, in Gauss' law, we need to develop a Gaussian profile. But in ACL, we need to build the Amperian loop. When we talk about loop, it is a line. And that particular line will be based on the coordinate system that we choose in the first step. Okay, due to this, I'm going to consider current, okay, a condition of my current coming out from a piece of paper. Okay, because now I'm going to transform this 3D into the 2D drawing. Okay, so I'm going to transfer this into 2D drawing. So now I'm considering that I have a charge coming out from my paper, so I note it as dot here. But if we consider the charge is flowing into the paper, this will be a cross. But now I'm consider at this particular point of view. So I'm looking at the top of this view. So what I can see is the charge is coming out from here. So this is my charge. Okay, and now I'm going to draw where this is my x axis and this is my y axis. Okay, as you can see here, we need to draw the Amperian loop. This loop will be based on the position or the location of H. Okay, let's say this is the particular location of H. Okay, where I want to find the H at this particular position. Thus, I draw the Amperian loop using this one. okay, where the current will be the center of this circle. Why circle? Because I refer to this cylindrical coordinate system. And this loop should be passing through the location of our H, and the current should be at the center of this loop. If the H at this particular point, thus we need to redraw the Amperian loop considering at this position. Okay, but now due to the position of H is here, thus this will be our Amperian loop. Okay, so this I can draw, this is my R. Okay, then the fourth step is we need to solve the Acl equation. Okay, the common or the general equation of the Acl is the integration, the closed integration of H dot dl is equal to I enclosed. Can you see that this equation is quite similar to the Gauss law? Okay, where in the Gauss law, it is the closed integration of d dot ds equal to q enclosed. But for the ACL, it is the closed integration of h dot dl equal to I enclosed. Okay, I'm going to denote this as my right hand side equation, where it's supposed to be left hand side. Left hand side equation. So this left hand side equation should be related to this diagram, okay, where this will be depend on the shape of our loop, okay, while this one I'll denote as our right hand side equation, and this right hand side equation will relate to the current inside the loop. Okay, I repeat, the left hand side equation we relate with the shape of the loop, while the right hand side equation is relate to the current inside this loop. Okay, continue to calculate the H. Okay, I'm going to take my left hand side equation, where this one is equal to the closed integration of H dot dl. Okay, and this equation must be based on the previous diagram. So in previous diagram, I do not know the exact information of our H. Thus, now I'm going to write it in the general term of H. And because we are using the cylindrical coordinate system, thus I can write my H as this one. Okay, plus H phi in the phi direction plus Hz in the z direction. Okay, where this one is represent our H. Okay, how about the dl? If you still remember, we have a diagram with a dot and there is a line or the Amperian loop. The dl supposed to be at the Amperian loop. So this is a dl. Due to this, the dl can be replaced by r d phi in the phi direction. Okay. Now, the dot product between r and phi will be 0. The dot product between z and phi will be 0. Thus, only this will be left. So that the equation will become phi is between 0 to 2 pi. Okay, and this one will be h phi r d phi. And this will become 2 pi r h phi. Okay, now we settle with the left hand side equation. Let's take a look at our right hand side equation where this one is equal to I enclosed, and refer to this particular diagram where inside the loop we only have I. Thus, this one is equal to I. So now we need to relate the left hand side and the right hand side. Okay, I can write here the 2 pi r h phi is equal to I. And now we want to find this h. Okay, so I'm going to write h equal to I over 2 pi r. Remember that we are solving in the phi direction, so this will become phi and this will become a vector. So now this is the final equation that we get, and compare with the one that you get using the biosavite. Does it same? Yes, it's same. So for the infinite condition, you can choose to use the biosavite's law or the ACL. So that's all for this video. Thank you.